All right, for the first problem here, for assignment number 12, find dy dx by implicit differentiation. So that means we're going to differentiate with respect to x, and I'm going to rewrite square root of xy as x to the 1/2, y to the 1/2. I think I just want to use product rule here instead of power rule and then chain rule. So maybe we'll start out differently, but so I'm differentiating with respect to x for both equations, and then I need to do power rule here. So first times derivative of the second. This is 1/2 y to the negative 1/2. Now remember, if you're differentiating, if you're finding the derivative of something that's not x, you need chain rule, which is dy dx. You multiply by the derivative of y with respect to x. So that's first times derivative of the second plus second times derivative of the first. The derivative of x to the 1/2 is 1/2, x to the negative 1/2. I don't need a chain rule there because it would be dx over dx, and that's 1. Okay, on the other side, we have another product rule. First times derivative of the second. The derivative of y is 1, dy dx, plus second times derivative of the first. Derivative of x squared is 2x, plus the derivative of 1, which is 0. All right. Our next step is to clean this up a little bit so that we can get our dy's on the same side. So let's see. I think I'm going to wait on the negative exponents. I'm going to keep them where they are. Is that what I want to do? Yeah, that's what I want to do. Okay, so 1/2, x to the 1/2, y to the negative 1/2, dy dx. And then this would be plus 1/2, x to the negative 1/2, y to the 1/2. And there's not a lot to clean up here. Equals x squared dy dx. Just make this plus 2xy, and I don't need the plus 0 anymore. All right, now it doesn't matter what side you move your dy's to, but if I put dy dx, if I move this term to the left side, and if I move this non-dy dx term to the right side, I would get dy dx. If I factor this out, I would get, let's see, so now I think I'll change my exponents around. So I would have from this term x to the 1/2 over 2 y to the 1/2. So I got rid of that negative exponent. And then there would be a minus x squared from that term. And then over here, we just have 2xy minus, because I subtracted this term over. So on this one, y to the 1/2 is on top, and 2x to the 1/2 is on the bottom. So I did a couple of steps in once. I moved my dy dx over and I factored it out. The reason we factor that out is so that we can divide by the parentheses and get dy dx isolated. So this is now 2xy minus y to the 1/2 over 2x to the 1/2 over x to the 1/2 over 2y to the 1/2 minus x squared. Now, if we have a problem like this, it's pretty slim. There is a pretty slim chance that they're going to leave their answer like this. They're going to want it to be simplified, or that it would be a simplified choice in a multiple choice. So let's clear out the complex fraction. So there's a denominator of 2x to the 1/2, and there's another denominator of 2y to the 1/2. So the common denominator there is 2x to the 1/2, y to the 1/2. And if you multiply by that LCD in the top and the bottom, you're multiplying by 1, so you're allowed to do that. And remember, you distribute that through. It should clear out the complex fraction and leave us with dy dx. All right, so 2xy times 2x to the 1/2, y to the 1/2, that's 4. X to the 1/2, or 3/2, y to the 3/2, minus, so here the 2x to the 1/2 are going to cancel, and we'll have minus y to the 1/2 times y to the 1/2, or just minus y. In the denominator, 2y to the 1/2 and 2y to the 1/2 will cancel, so I'll just have x. And then down here, I will have minus 2x to the 2.5, because you add your exponents. 2.5 is 5 over 2. Y to the 1/2. And I could factor a y out and factor an x out, but there's not really any reason to. Nothing would cancel or simplify. So that's my final dy dx. All right, and I just want to verify. Yeah, okay. Sorry, just wanted to check that. Okay, so number 11 has the same set of instructions, a little bit less complicated as far as the number of steps we'll need to simplify. So we're still differentiating with respect to x, both sides of the equation. I like to put my angles in parentheses to remind myself that we're going to need to chain rule because there's a nested expression inside of a cosine function. So take the derivative of both sides. The derivative of sine x is cosine x. The derivative of 2 cosine is minus 2 sine of the angle, 2y. And then remember, you've got a chain rule because you have a 2 cosine function. We took the derivative of that. And then you also have a 2y on the inside. You need the derivative of that. So the derivative of 2y is 2, and then dy dx. If we're differentiating with respect to x, we've got to have that chain rule in there, the derivative of y with respect to x. The derivative of the constant 1 is 0. Okay, so solving this, I am going to add my dy dx term to the right so I don't have negatives. Again, that part does not matter. It's just personal preference. I also realized that I have a 2 and a 2, so I'm going to make it minus 4 sine of 2y dy dx. And then I'm going to divide. Oops, and that should be plus. Sorry, not negative. Goodness. Okay, so yeah, because I added that over. Okay, so it's cosine of x divided by 4 sine of 2y. That equals dy dx. Okay, number 15. Take the derivative with respect to x of both sides. Okay, the derivative of y is just 1, or you could also just say, oh yeah, that's just dy dx. 1 times dy dx, or just dy dx. Here we have the sine of something. So what's the derivative of sine? Cosine of the angle. And then what's inside of the parentheses? An xy. So we need to multiply by the derivative of x times y. Now that needs product rule, so be careful there. So first times derivative of the second plus second times derivative of the first. We have some stuff to clean up. The only way to free up this dy dx is if we distribute our cosine through. So dy dx equals, I'm going to put x cosine of xy times dy dx. And then remember, you're also multiplying that by this y out here. So plus y times cosine of xy. Okay, so we can get our dy dx's on the same side. I'm going to subtract this over to this side and factor out a dy dx at once. So this term would become 1 minus x cosine of xy. You don't have to skip. I tend to do that in the 2 steps in one just because I can keep track of it pretty well, and I'm being a little bit lazy, I guess. But again, if you can keep track of it, it's fine. If you get confused about that, then just show one extra step of just you moving this term over and then factoring out the dy dx. The last step is to always divide. Y cosine of xy divided by 1 minus x cosine of xy. And that's as far as that can go. Okay, number 25, find dy dx by implicit differentiation and evaluate the derivative at this point. All right, so again, we're going to differentiate both sides with respect to x. any variable that's not an x will get a dy dx multiplied to it. So I take the derivative of both sides. The derivative of x to the 2/3 is 2/3 x to the negative 1/3. The derivative of y to the 2/3 is 2/3 y to the negative 1/3 times dy dx. And that's equal to 0, which is the derivative of 5. Okay, I need to get this dy dx by itself. So I'm going to leave it on this side. I guess I could rewrite my exponents, huh? Let's see. So this is 2 over 3y to the 1/2 times dy dx equals negative 2 over 3x to the, oh, sorry, not 1/2, 1/3. Back here, 1/3, sorry, and 1/3. So I subtracted negative 2 over 3x to the 1/3, and then I'm going to divide. But remember, dividing by a fraction is really multiplying by the reciprocal of said fraction. I keep wanting to write 1/2. So all these coefficients cancel, and you're left with negative y to the 1/3 over x to the 1/3. Or you could also make that the cube root of negative y over x, but I'm just going to leave it like this. And then evaluate the derivative at the given point. So evaluate dy dx at the ordered pair 8, 1. So we're putting in 8 for x and 1 for y. So this is negative cube root of 1 over the cube root of 8. Negative 1 over 2 should be my final answer. All right, same instructions for number 28. So first we take the derivative with respect to x of x times cosine y, and we take the derivative of a constant. Remember, you need product rule here. So first times derivative of the second. The derivative of cosine is negative sine, and the derivative of y is dy dx. Plus second times derivative of the first is equal to 0. I'm going to add, because I see dy dx is negative, I'm going to add it to the right side. So I'm going to leave cosine of y over here. I am adding dy dx, and it's getting multiplied by a negative x sine y. Nope, by a positive. Goodness. How many mistakes can I make today? So by a positive x sine y, because I'm adding that over. And then I divide. So cosine of y over x times sine y. That's the dy dx equation for the derivative. And now we can evaluate dy dx at the point 2 pi over 3. So that's the cosine of pi over 3 over 2 times the sine of pi over 3. Okay, so unit circle trig. Remember, at pi over 3, the ordered pair is an x coordinate of 1/2, radical 3 over 2. So cosine is 1/2. And this is 2 times radical 3 over 2, which is really just 1/2 over radical 3. And that is really just 1 over 2 radical 3. And I'm not going to bother rationalizing my denominator. You don't have to for your AP exam, but you could if you want to. All right, famous curves. This is kind of cool. Witch of Agnesi, and here's a cissoid. There were more on the textbook page if you look at it. Find the slope of the tangent line to the graph at the given point. So we need to take the derivative of this equation and evaluate at that point. I think I'm going to distribute the y squared through. So I want to take the derivative with respect to x of 4y squared minus xy squared. I don't know if that makes my life any easier or not. It's just kind of my instinct to do that if I see something simple to distribute through. And then the derivative of x cubed on the other side. So the derivative of 4y squared is 8y dy dx. And then when I'm doing a product rule and there's a subtraction here, I always think of, you know how we say first times derivative of the second? So I consider the first function to be negative x and the second function to be y squared. And that way I don't have to remember to distribute a negative through at the end. So if you do it like that, then it's first times derivative of the second, 2y dy dx, plus second, y squared, times derivative of the first. The derivative of negative x is just minus 1. So these are the correct signs. This is what I would have if I did product rule and then distributed a negative through. So I find this to be more efficient. And then on the other side, it's equal to 3x squared. No chain rule required because this is in terms of f and we're differentiating with respect to x. All right, so the dy dx's are already on their same side. I'm just going to add y squared over to this side and then factor out dy dx. So that's 8y minus, make that 2xy, equals 3x squared plus y squared. And dy dx equals 3x squared plus y squared all over 8y minus 2xy. Again, I could factor y, or 2y, I guess, out of the denominator, but it doesn't help me in any way to do that. Nothing cancels, so I'm just going to leave it as it is. And then we need to evaluate the points at 2, 2, or evaluate the derivative, at the point 2, 2. So that's 3 times 4 plus 4 over 8 times 2 minus 2 times 2 times 2. So 12 plus 4 is 16. 16 minus 8 is 8. So derivative is 2, which I believe that, right? There's the tangent slope. It seems like it could be a slope of positive 2. Okay, now we're skipping to 48. So find the second derivative in terms of x and y. So what that means is you can't still have dy dx in your final answer. All right, so we are going to take the derivative with respect to x of both sides. Okay, the derivative of 1 is 0. And then again, treat the first function as negative x and the second one as y. So first times derivative of the second, dy dx, plus second times derivative of the first. Derivative of negative x is negative 1. And that equals the derivative of x is 1 minus the derivative of y, dy dx. Okay, we need the dy dx's to be on the same side. So I think I'm going to add dy dx over here. I'm not skipping my step this time because I feel like I'm going to screw something up. So I have 1 over here. I'm going to add y over here. Okay, so if I factor out a dy dx, I would have 1 minus x. All right, so dy dx is equal to 1 plus y over 1 minus x. Now, you're not finished at that point. You have to find the second derivative. So let me bring this up here so I have room. All right, now here's the equation that we have so far. Here's dy dx. We want to take the derivative with respect to x of this equation because that will give us the second derivative. All right, so on this side, I've got my second derivative of y with respect to x. On this side, if I want to take this derivative, because I can't simplify or divide out the rational, I've got to do quotient rule. So low, d high, the derivative of 1 plus y is just dy dx, minus high, d low, the derivative of 1 minus x is negative 1, all over low, low, 1 minus x, the quantity squared. So here's the key to this. This is where people tend to kind of get lost or forget what to do. We're not finished because we need to get rid of dy dx. And remember, we have an equation for that, dy dx. We have an equation in terms of x and y, which is what we're trying to get to. So we can sub that in, and some nice cancellation will happen when we do that. We get 1 minus x times 1 plus y over 1 minus x. So those will cancel. And then how about instead of minus negative, we just make this plus. I don't need parentheses anymore then around 1 plus y. And down here we have 1 minus x, the quantity squared. So yeah, these 1 minus x's cancel. These problems are almost always like that. Something does tend to cancel or simplify quite a bit. And then in the numerator, 1 plus y plus 1 plus y is 2 plus 2y over 1 minus x, the quantity squared. So that's our second derivative equation. All right, for the next set of points, I did the calculator part here, so I'm going to leave this up. Find the equations of the tangent line and the normal line to the circle at each given point. And it tells us here, the normal line at a point is perpendicular to the tangent line. And then use a graphing utility. So you can see whatever I got here, here's a tangent line, and here's a perpendicular line to it. And here's another tangent line, here's a perpendicular line. So we need to come up with a dy dx since we're looking at slopes. So take the derivative with respect to x of both sides of this circle equation. So the derivative of x squared is 2x. The derivative of y squared is 2y dy dx. The derivative of 25 is 0. Okay, so dy dx, let's see, when we solve for this, we're going to get negative 2x divided by 2y. So it's negative x over y. Okay, we're trying to come up with a tangent line equation and a normal, a perpendicular to the tangent line equation. So first we need to know what is the slope at each of these points. So evaluate dy dx at the point 4, 3, and you get that the slope is negative 4 over 3. Okay, so if I want a tangent line equation, then I'm going to get y minus 3 equals negative 4 thirds times x minus 4. There's the tangent line. If I want the normal line, the perpendicular line, I just use the same point, but now I know that the perpendicular slope would just be positive 3/4. All right, so at 4, 3, at this one, we had our tangent line and the perpendicular line. All right, so that's one set of answers. Now do the same thing for the other point. The other thing is evaluate dy dx at negative 3, positive 4. So putting in for x, that's 3. Putting in for y, that's 4. And again, the tangent line would be y minus 4 this time equals 3/4 x plus 3. And then the normal line, the perpendicular line, would be y minus 4 equals negative 4 thirds x plus 3. It said to verify on the graphing calculator, so I did. Also, to get a circle to look like a circle, if you choose zoom square, which is one of the options in the middle there, it makes everything look kind of nice. All right. Find the points at which the graph has vertical or horizontal tangent line. This is a pretty common question, maybe not with this particular function. This is a conic of some sort, right? Probably an ellipse. Yeah, because the two squareds are positive. This is an ellipse. We could do all that fun complete the square stuff and just graph it and figure it out, but I'm going to do calculus instead. All right, so we're going to use a calculator for part of this just because the number crunching. Not that it's impossible without a calculator, but it's a bit tedious. So, all right, so I am showing that I'm taking the derivative with respect to x on both sides. Again, it is not required to show this step, but if you can see, I've done that as my first step for every single problem. It's good for your brain sometimes to have a like when the directions say this, the first thing I always do is this. Like, it's nice to write this down, and then maybe that triggers your brain into the next step. All right, so let's take derivatives. So this becomes 50x. This becomes 32y. Remember to chain rule, dy dx. Plus 200 minus 160, again, dy dx. 400 becomes 0. And then that's equal to 0. So let's see, dy dx, if I factor that out of these two terms, I get 32y minus 160. And that's equal to, it bothers me to have a bunch of negatives everywhere. So actually, I'm going to keep the 50x plus 200 over here. This really does not matter. It's just a personal preference thing. I'm moving the dy dx's over to this side. So when I factor out dy dx, it's going to be positive 160 minus 32y. Again, you don't have to worry about all that. That's how I want to show my work. So here is our dy dx equation. So now what do we do? The problem says find the points. We're going to need xy points. Answers for x and y, for which the equation has a vertical or a horizontal tangent line. So let's start with vertical. There is a vertical tangent. You usually get a point on the AP test for writing this, by the way. So just writing this much of the problem, even if you forget everything else. There's a vertical tangent if dy dx is undefined. And how does this rational expression be undefined? If the denominator, 160 minus 32y, if that equals 0. All right, now if we solve this for y, 160 divided by 32 is 5, right? Because 150 plus 10. So that's 5, or you could use a calculator. And I need to find the x. What is x when y is 5? So go back to the original curve here. The only way for me to know what is x and y is 5 is to plug in 5 for the y's and see what x comes out to. So that's 25x squared plus 16 times 25. This is where I am going to use a calculator. Plus 200x minus 160 times 5 plus 400 has to equal 0. All right, so let's do the math on this. 16 times 25 minus 160 times 5 plus 400. So I'm just doing the math on all of the non-variable terms, and it adds up to 0. Okay, so really all we're going to have left is 25x squared plus 200x, and all the numerical terms went away, equal to 0. We can factor this. Factor out a 25x, and you're left with x plus 8. And so the two solutions for x are 0 and negative 8. And remember, the question said, tell me the points where there are vertical tangents. So there are vertical tangents at 0 for x, 5 for y, and negative 8 for x, 5 for y. Now there's a second part to this question. What about horizontal tangents? So you get a horizontal tangent when the slope dy dx is equal to 0. And with a rational expression, that's when the numerator is equal to 0. So 50x plus 200 is equal to 0. And that happens when x is negative 4. And then same idea. Now you've got to plug in negative 4 into the original curve for x and solve for y. So it's going to be 25 times 16 plus 16y squared plus 200 times negative 4 minus 160y plus 400 equals 0. I'm going to kind of guess that these terms cancel out again, but it was 25 times 16 minus 800 plus 400. Oh, come on. Minus 800 plus 400 is just minus 400. Okay, yeah, so that's 0 again too. So we get 16y squared minus 160y equals 0. Factor out a 16y. And we get y equals 0 or y equals 10. So there are horizontal tangents at, make sure you're doing xy. When x is negative 4, y can be 0. And when x is negative 4, y could be 10. So that's a really long problem. We do have things like that, and like that's a pretty common part of a free response question. Maybe not this whole thing, but either finding vertical tangents or horizontal. Okay, same thing for this one. So I'm going to cheat a little bit and just say take the derivative with respect to x. Okay, da. So this is 8x plus 2y dy dx minus 8 plus 4 dy dx plus 0 equals 0. Let's factor out dy dx. That's 2y plus 4. If we move the other terms to the other side, we'd have a positive 8 and a minus 8x. And we're going to be able to factor a little bit. I can factor an 8 out. I do want to do that this time because I can also factor a 2 out of the bottom. And that gives me a slightly smaller number to work with. 4 times 1 minus x over just y plus 2. This is still the same question, same type of question. So find vertical tangents and horizontal tangents. So again, here's another thing where we just did this, but it's good to get in the habit of writing vertical tangent when dy dx is undefined. And that happens when y plus 2 equals 0. And that happens when y equals negative 2. I need the point. So now that I know y is negative 2, see what x is. So you get 4x squared plus 4 minus 8x minus 8 plus 4 equals 0. I think I can handle this without a calculator. Plus 8 minus 8 is gone. Factor out of 4x. That leaves you with x minus 2. So x is 0 or 2. And the y coordinate was negative 2. So there are vertical tangents at 0, negative 2, and 2, negative 2. I'm trying to be careful that I don't answer yx instead of xy. Horizontal tangents when dy dx equals 0, and that happens when 4 times 1 minus x equals 0, which is just when x equals 1. Plug 1 in for x this time. So that would give me 4 plus y squared minus 8 plus 4y plus 4 equals 0. All right, so 4 plus 4 minus 8, factor out a y. So y equals 0 or 4. And again, answer with xy. So charge up my pen here. So we have horizontal tangent at 1, 0, and 4, 1. 1, 4. See, I almost mixed it up there. All right. You don't want to do all that work and then get the answer, lose 1 point because you mixed up your coordinates. That would be silly. Okay, and then the last problem here. Differentiate with respect to x. And then for part B, differentiate with respect to t. And we had this a little bit in the notes, but not much. So with respect to x means, for part A, derivative with respect to x. This is what we've been doing for the entire homework. So I get 4y dy dx minus 12x to the third equals 0. Anything that's not an x gets that little chain rule on it. Oh, sorry, weird parentheses there. Okay, And then I could solve this one for dy dx. So I could say, okay, dy dx is add 12x to the third, divide by 4y. So it's 3x to the third over y. That one I could simplify. Maybe I don't have to, but I did. Now, if we differentiate with respect to t, so it'd be like d dt of 2y squared minus 3x to the fourth, or maybe we haven't done this in the notes. Now that I'm thinking of this, if we have not done related rates, then this is a preview of what we're doing probably in tomorrow's notes. Okay, so neither of these variables are t, so they're both going to need chain rule on them. So here's how we do that. Still, the derivative of 2y squared is 4y, but instead of dy dx, I'm going to write dy dt. And then the derivative of negative 3x to the fourth is minus 12x to the third. And instead of not writing anything, this time the variables don't match up. So I'm going to write dx dt. Chain rule there. Still equal to 0. Now, since these are not the same, dy dt is not the same as dx dt, we can't really do anything else with this equation. I suppose I could divide by 4. I could divide both sides of the equation by 4. But that's about all that I could do. Oh, dy dt. That looks really terrible. Hold on. Fix that. So yeah, the only thing I could do is say, all right, divide both sides of the equation by 4, and you get something like this. In our problems tomorrow, our related rates problem, we will have information that we plug in for one or the other, and then we can isolate the unknown. All right, this was a long homework assignment, so good job if you made it all the way through. Let me know if you have questions.